All right, day 26. Today, we're unpacking a really powerful technique for finding hidden patterns in your data. It's called Principal Component Analysis, or just PCA.
So, have you ever opened a data set with, say, 100 columns and just felt lost? You don't know where to start. That feeling, it's not just you. It's a real statistical challenge, often called the curse of dimensionality.
Because with all those features, you get a ton of noise. The big question becomes, how do you simplify things without accidentally throwing away the most important information?
Well, that's exactly what PCA helps us do. By the end of this, you'll get the core idea of how to reduce that complexity and let the most important patterns in your data shine through.
Now, your first instinct might be to just start deleting columns, but that's a bit like throwing darts in the dark. A much better approach is to find a new perspective, a better angle from which to look at your data. Here's an analogy. Imagine you have a complex 3D object, like a chair. If you shine a flashlight on it, the shadow it casts on the wall can look completely different depending on the angle of the light. From one side, it might be a confusing blob, but from just the right angle, the shadow clearly shows the shape of a chair. PCA is the mathematical way of finding that perfect angle for your data. See, on its original axes, your data might just look like a big, messy cloud of points. Many of your variables are probably correlated, meaning they contain redundant information. PCA essentially rotates that whole cloud of data. It creates a brand new coordinate system where the new axes, the principal components, are aligned with the directions where your data is most spread out. That very first new axis is called Principal Component 1, or PC1. It's drawn straight through the data along the direction of the greatest spread, or variance. You can think of it as the main storyline of your data set. It's the single dimension that holds the most information. Then we find the second principal component, PC2. It's designed to capture the next biggest chunk of variance. But, and this is crucial, it has to be perfectly perpendicular, or orthogonal, to PC1. This little rule ensures that our new features are completely independent of each other. They're not repeating information. So how does PCA actually find these best angles? It's not magic. It follows a pretty clear recipe. The first thing you have to do is standardize your data. This just puts all your variables on the same scale, so one feature with huge values doesn't dominate the others. Once that's done, we move into a bit of linear algebra. We compute something called the covariance matrix. It sounds technical, but it's just a grid that summarizes how every variable moves in relation to every other variable. It tells us which ones tend to go up together and which ones move in opposite directions. This is how we map out the redundancy in the data. Next, we find the eigenvectors of that matrix. Now, that word can sound intimidating, but the concept is very intuitive. The eigenvectors are simply the directions of our new axes. They are the principal components. Going back to our flashlight analogy, the eigenvectors tell you exactly which directions to point the light to get the most meaningful shadows. And for every eigenvector, there's a corresponding eigenvalue. An eigenvalue is just a score. It's a number that tells you how much information, how much variance is captured along that eigenvector's direction. So a bigger eigenvalue means you found a more important principal component. And this is where it all clicks. The eigenvalues let us rank each component by importance. You'll often find that the first one or two components are the real superstars. For instance, PC1 might capture, say, 85% of all the variance in your data, and PC2 might capture another 10%. That means together, those two components hold 95% of the story. This is the power of PCA. We can now focus on just those two dimensions and safely ignore the rest. So where do people actually use this? Well, it's a go-to tool for data visualization, letting us squash high-dimensional data down to 2D or 3D so a human can actually look at it. It's also a standard pre-processing step in machine learning to make models faster and more robust. It's even a core idea in image compression and noise reduction. It's all about finding the signal in the noise. Let's look at a concrete example. Here's a medical data set for breast cancer diagnosis. It has a lot of features, things like tumor radius, texture, smoothness. If you just look at this table of numbers, it's impossible to see any patterns. But we can run PCA and distill all of those different measurements down into just two principal components that capture most of the important information. And here is the result. When we plot that same data on our two new axes, a clear pattern just pops right out. You can now see two distinct clusters that were completely hidden before. This is what it's all about, revealing the hidden structure in your data to make it easier to understand and easier to use. So, to sum it all up in a single sentence, PCA transforms a complex set of correlated data into a smaller set of simple, uncorrelated components that tell the most important part of the story. The key takeaway is this: when you're faced with overwhelming complexity, the answer isn't always to throw information away. Often, it's just to find a better point of view.